Alrighty then. So, we just finished talking about the mole. You know more about the mole now than you ever wanted to know in your entire life. I know that. You don't have to convince me otherwise. But now, we're going to figure out how to use the concept of the mole to deal with the actual amounts of stuff in chemical reactions. So, what we have in front of us is an equation, which we're going to balance, and then we are going to come up with all the possible mole ratios in the equation that we see. Now, mole ratios, like I wrote over here on the right side of the page, are used to relate the amounts of different substances in a chemical reaction. So, for instance, we can know if we have a certain amount of aluminum in this particular reaction, how much oxygen we're going to need to figure that out. Now, first thing we need to do is to balance this equation. So, as always, I'm going to go ahead and make a chart because I like charts. So, we're going to make a chart with aluminum and oxygen. Two elements, no weighting. So now, I'm just going to go ahead and kind of quick fire through this just to save some time here. So, if we put a 3 in front of, no, actually, let's put a 2 first in front of oxygen, in front of aluminum oxide, rather, on the right side to make things even. So I'll go ahead and put a 2 there. That changes this to 6, changes aluminum to 4. If we go on the other side, we can change aluminum to 4 really easily, and then, to give us 6 oxygen atoms, we can put a 3 in front of oxygen. So, if you'll allow me to get rid of this chart in the interest of saving some space, I just want to talk about a little bit what this equation tells us. So, there's a lot of things that it tells us, and we could go through each and every one of the things that it tells us. But for now, we're going to keep it simple, and we're just going to talk about things in terms of moles. So, this equation tells us a few things. It could tell us that 4 atoms of aluminum come together with 3 molecules of oxygen to form 2 formula units, and I'm only using that term because it's an ionic compound, so I'm trying to be consistent, of aluminum oxide. So that's one thing that it can tell us. Now, the other thing that it can tell us is, it could tell us things in terms of masses as well, but we'll save that for the next podcast. The thing that these coefficients tell us is the number of moles of each of these substances that actually has to take part in this reaction. The number of moles of aluminum and oxygen that we need, and the number of moles of aluminum oxide that we get in the end. So, in this case, if we're thinking about things in terms of moles, and remember, a mole is 6.02 times 10 to the 23rd particles of anything, whether it's aluminum or oxygen or aluminum oxide, that becomes something that we can kind of look at in common between all of these substances. And if we want to find out information about one of the substances, and we only know information about another substance, we can use the relationships between the moles of these different substances to figure that out. And that's where the mole ratio comes in. Now, really, most of stoichiometry, which we're about to start, involves the same kind of mole conversions that you did before. So if you were comfortable with the 2-step mole conversions that we did before, you're not going to have a problem with any of this. If you're not comfortable, I would highly recommend spending some time after school, getting some extra help, making sure you're solid on that stuff. But the only extra step, literally, the only extra step here is the mole ratio. So, mole ratios are written as fractions. Now, you'll remember that in our grids, we basically set up a series of fractions to cancel the units we don't want, and to to end up with the units that we're looking for in the problem. So in this case, the units that we don't want, the units that we want to eliminate, are the moles of one particular substance, the substance that we're given in the beginning of the problem. And the thing we want to get is the moles of the other substance. So I'm just going to set up a series of mole ratios, because the question asks us to find all the possible mole ratios in the equation below. So we've balanced it, And to get our mole ratios, all we have to do is we use the coefficients in the balanced equation. You'll probably notice as we go that some of these can be reduced to simpler form. Don't worry about it. Just use what you have, use those coefficients as they are. 2 over 4 is going to be the same as 1 over 2, and just work with it. So, to start, let's compare aluminum and oxygen. So, I could say that we have 4 moles of aluminum for every 3 moles of oxygen. I could use the mole ratio as 4 over 3, just like that. Or I could flip it. I could say that we have 3 moles of oxygen for every 4 moles of aluminum. Both of those things are true because we're looking at the balanced equation that tells us so. Now, if we want to compare aluminum to aluminum oxide, let's say, Al to Al2O3, that's also pretty easy because, again, we just use the coefficients in the balanced equation. 4 moles of aluminum on top, and let's say 2 moles of Al2O3 on the bottom. Now, if we had to make a conversion in the other direction, we would just use the other conversion factors. So we start on top with 2 moles of Al2O3, and on the bottom, we have the same 4 moles of aluminum. Notice that these numbers never change. They're always going to be the same, and they're always going to be based on the balanced chemical equation and the coefficients for each substance that you find in it. So, now we have to compare oxygen and aluminum oxide. So, our first one would be 3 moles of oxygen over 2 moles of aluminum oxide. Again, numbers don't change. So, our final conversion factor is just the reverse of that. We're just going to flip it. 2 moles of aluminum oxide over 3 moles of oxygen. Now, right now, these probably look a little weird and, frankly, a little useless because they're just a bunch of numbers. You'll see in the next podcast why this matters and why it's also so important. And I'm going to circle this point down here just to really emphasize it. How important it is to always write the formula of each substance. You want to keep track of what you actually have so that you can convert it to something else. Like I said, right now, this may seem pretty silly. I used to do a thing where we wrote out about 17 different mole ratios, and it really didn't do much good because you weren't using them. So, this is all we're going to do with this, and in the next podcast, you'll see how we can actually use these mole ratios as conversion factors to actually convert between the moles of one substance and the moles of another. Thanks for watching.